If you've been on a roller coaster that has a loop, I guarantee it wasn't a circular loop, because circular loops would cause injury to most of us, and for some of us, it would be terminal. Read along with me. It says this, example one. This question is really cool. I like it. I'm not saying I like it, I like it, I like it. I like each part of it. It's just so long, I would never give this to you as a test question, but each subpart of it, Matt, to me is fair game. A roller coaster barely makes it around a vertical loop of radius 4 meters. A says, find the minimum height that the roller coaster needs to start from at the top of the hill to just barely make it through the loop. Okay. I guess this wants us to find that. Well, they said height, not displacement. Any thoughts on how I might want to approach this? What tools might I use from my toolbox here? I think I see a change in height, a change in speed, and a yucky curvy path. I think I'm going to use the law of conservation of energy, G. And here's where I'm going to get clever. I'm going to let initial be right here, but I'm going to let final be there, top of the loop. And I'm going to say to myself, well, okay, the law of conservation of energy G says K E initial plus P E initial equals K E final plus P E final. And we'll ignore heat. We'll assume we start from rest. So let's get rid of that. But nothing else is zero. We're not on the ground, initial or final. And we certainly don't want to be at rest at the top of the loop. Then we'll come crashing down. That's not good. So I'm going to substitute in the equations at least. I'm going to say, okay, mgh initial equals a half mv final squared plus mgh final. Well, can little kids and grown-ups go on this ride? Yeah, they'll die, but they can go on this ride. M's cancel. All right. Let's see if we can substitute some other stuff in. I now want to target this v squared. Now that's the v right at the top right here. Well, at the top of the loop, what path am I tracing out? Oh, you know what this might be a good job for here? Let's try a free body diagram. What are the forces acting at the top of the loop? Get the obvious one. We have gravity down. And then we also have a normal force. Although, if we're just barely making it through the loop, what did we say if you're just barely making it through the loop? How big is the normal force exactly as a number if we're trying to do this minimum? Yeah, I'm going to say that equals 0. So at the top of the loop, Maddie, who's winning? Who's losing? In fact, I'm going to have this. mg equals mv squared over r. Why did I know to use the v? Because I'm trying to figure out something for the v down over here. In fact, I think that's going to be vf squared over r. In fact, I wrote over 2. It's over r, Mr. Dueck, not over 2. Maddie, m's cancel again, yes? Let's get the v squared by itself. I was going to get the v by itself, but then I noticed it's a v squared over here. Why don't I get the v squared by itself? How would I move the r over? And I'll get this. V final squared is GR. That means where I see the VF squared in the energy equation, what can I replace it with? So I'm going to do that on the next line here. The G and the H initial will drop down. I'll get 0.5 GR. and then plus, all right. Well, the G drops down. That H final, do you agree with me? That's H final. That you okay with that, Paul? Okay, Paul, we're going to get clever. Are you ready? I'm going to ask you several questions in a row. Your hint is they're all going to end up with the same answer. What do I call the distance from here to here, from the middle to the center? It starts with the letter R. Loud and proud. How far from here to here? R. How far from here to here? How far from the middle down? How far from the middle up? How big is the height in relation to R? Hey. So what can I replace this H final with? 2R. And interestingly, I have this. GH initial equals, do you know what 0.5 GER plus 2 GER is? They're like terms, right? It's 0.5 GR plus 2 GR. Oh, and also, Matt, is there a G in the left-hand term? Is there a G in the right-hand term? What happens to the G's? Would this roller coaster work on any planet, not just Earth? That's what that means. If the G's cancel, you found something that will work on the moon, on Mars, wherever. And this is our answer. It's kind of a neat answer. If you want to make it through a roller coaster loop that's circular, the minimum height is 2.5 times the radius. I love this question. I'm not saying I like this question, like this question. I'm saying I love the fact that look at how complicated we started out. Let me scroll up so I have all my circular motion stuff as well. Look at how complicated we started out with, and we end up, Raisa, with a bunch of stuff canceling or being substituted. You get 2.5 times the radius, and you'll make it through the circular loop. So let's actually crunch that now. What was the radius? I've scrolled down. Was it 4? Yeah. So 2.5 times 4. 10, I think. Double check me, but yeah. I would imagine if you're a roller coaster ride designer, in the same way all of you have memorized F equals what, they would probably have memorized, oh yeah, better make sure we have a height of at least that. But this is for a circular loop, a loop that's a perfect circle. And I started out class by asking, how many of you have written a circular loop? And then telling you all to put your hands down because none of you are dead and none of you have. Callum, what does the second part want me to find? Part 2. Where? The question tells me, I'm pretty sure. Where does it want me to find the normal? I think it does. Bottom. Yeah. It wants me to find the normal force right here. Okay. Well, you know, this is a good job for free body diagram. Okay. What are the forces acting right here? Get the obvious one. Which way? Down. What else? Normal force pointing up. Who's winning? Who's losing? What's that going to equal? What path are we tracing out right at the bottom there? A circle. So it's going to look like this. Normal force minus mg equals mv squared over r. Draw a little line. I'm going to do conservation of energy GG again, but this time, instead of letting initial be the top of the loop, I'm going to go like this. Or sorry, instead of letting final be the top of the loop, I'm going to go finals right here. Why? Because now I can use conservation of energy, and I'll bet you I can get an expression for v squared at the bottom of the hill, which would be v squared right there, which would be v squared right there, which would be v squared when we hit the loop, which is also v squared at the bottom of the loop. Follow the argument? So let's again go ke initial plus pe initial equals ke final plus pe final. We'll again assume we're starting at rest. Oh, and this time we're at the bottom, so the final potential energy is 0. Yay! Callum, what's the equation for kinetic energy from last unit? So this will be a half mv final squared. Potential energy, well, it's going to be mg. Now, I was going to write h initial, but wait. 2.5 R. Let's do that. Callum, is there an M on the left-hand side? Is there an M on the right-hand side? Can little kids and grown-ups still go on this ride? I think that they'd want to, but yes. I'm going to get the v squared by itself because this v squared is this v squared. I'm going to times by 2 to get rid of the 1/2. So I'm going to go times by 2 times by 2. On the left-hand side, I'm going to get 2 times 2.5, which I think I can do in my head. So what's 2 times 2.5? I agree. I'm going to get 5 gur, and also, hello, old friend. I probably set this up right if I got my gur again. That equals vf squared. So over here, where I see the v squared, what can I put in there? 5 gur. I'm going to get this. Normal force. By the way, how would I get the normal force by itself, Callum? How would I move the mg over? Yeah. So I'm going to have m. I'm going to have, instead of v squared, 5 gur over r. There's mv squared over r. Is that okay? And then what did you say I'm going to do with that mg? Add it. Oh, in that first fraction, Tommaso, is there an r on the top? Is there an r on the bottom? So I'll take that, and I get this. The normal force equals 5 mg's plus 1 mg. What's 5 mg's plus 1 mg? What's your normal? What's the one that all of you are used to exactly? What are all of you feeling your chair pushing up with right now? You're pulling 6 G's at the bottom. 6 G's is pretty high. That's on the threshold of already starting to maybe whiplash, pull some muscles. And in fact, the very first circular loops, by the way, that's assuming we're barely making it through. So that's the minimum G's. You probably in real life need to give yourself some speed coming over that first hill. KE initial wouldn't be 0. You'd want to build a big safety margin to get through that loop instead of barely making it over the top. So you'd be pulling 7 G's, 8 G's, 12 G's. The original, as far as I know, the original Loop the Loop coaster was called the Shoot the Chute. It was at Coney Island. I think it was in the 1880s. And all it was, you climbed a big high ladder, got in like a mining car, went whooshing down the hill, and at the bottom there was a circular loop, and then you went skidding to a stop. That's all it was, and people lined up for hours. They loved it. But they also had permanent nurses and ambulances stationed at the bottom. People got injured all the time. But in the 1880s, that was great! Who cares? So there were a few coasters at the turn of the last century, like the 1900s. They were built with circular loops. And the problem is, Callum, you're pulling at least 6 Gs, maybe more. So nobody builds coasters with circular loops. Did I go into it on the next page? I can't remember. No, I didn't. Instead, we build what's called a clothoid loop. And a clothoid loop is much more teardrop or skinny shaped. And the skinnier it is, the fewer the G's that you'll pull. So the very first steel coaster with loops, it's still at Six Flags Magic Mountain in California. I'm blanking on the name. I've been on it. It's got 3 loops, and when you look at them from the side, they're really tall and skinny like this. And it's honestly kind of meh. I mean, it's nice to go upside down, but the G's are meh. The closer the loop from the side looks to a circle, the more G's you're going to pull. Who's been on California Screaming before at Disneyland? Okay. Now that one, when you stand from the side, it really looks like a circle. However, part of it is an optical illusion. They deliberately put it right in front of a big picture of Mickey Mouse, but they've distorted Mickey. They've made it look more like that, but your eye isn't used to seeing Mickey look like that. Your brain isn't used to seeing Mickey look like that. So your brain makes it look more circular, which is why that loop looks more circular. But that's the ride that I pull some serious G's on. Whenever I go on that loop, I'll do one of 2 things. I'll either try holding my arms out, and when I'm in the loop, I'll just try moving them up and down. Or right before I hit the loop, I'll lean forward and then see if I can straighten my neck and my head out in the loop. And usually I can't. But most of the other loops, either it's a corkscrew, where your head and your heart are in the middle of the axis of rotation on that weightless area for fake gravity, so your heart and your head can handle that okay. That's what the corkscrew loops do. That's why they can do those pretty fast. But if it's a big full loop like this, it's almost always shaped much more like that. Just saying. So I'm not saying I like this question because there's a lot of work here. There is one like this in the Ultimate Review, but honestly, if you happen to remember that it's going to be 2.5 times the radius, you can get there in one line if you remember that obscure tidbit. I would say, to me, conservation of energy is still fair game. Asking you to come up with a free body diagram at the top of the loop, that's fair game. Asking you to find the normal force at the bottom of the loop, that's fair game. Doing all of this in one question, I'm not going to do that. It's just too much writing. Although I'd love to, because it's roller coasters, it's loops, and it's dear to my heart. I'm not going to do that. Okay. What's your homework? I'm not going to assign anything here. Instead, you're going to get a couple of take-home quizzes, and then I got some cool videos to show you. But you're going to have most of class to work on the quizzes.